as our next presenter. Allan, can you do a mic check for us?
Hello, can you hear me?
Yes, sir, we can.
Perfect. Well, thank you very much for the opportunity to speak today. We built Guru to automate the laborious parts of digital engineering and operations tasks to enable a person to focus their mental energy and time on things that matter, not searching cascades of menu bars for the thing they want to do. For example, in this presentation, we'll focus on setting up computational fluid dynamics simulations. Next slide, please. Just about a month ago, there was a new executive order calling for truth-seeking AI. We have built a hierarchical system that we're going to present today in order to accomplish just that. And my personal opinion is one of the ways a person can predict the future of where AI is going is to read some literature from decades ago. I'll give two examples real quick. Barr's global workspace theory proposes the consciousness function like a global workspace in the brain, where multiple specialized modules, for example, perception, memory, compete for access. Only one piece of information gains the spotlight at a time, becoming conscious and broadcast to other modules for integration and action. This explains how diverse brain processes unify into coherent conscious experience. And Minsky's Society of Mind from the 1990s theory proposes that the mind is a collection of many small specialized processes or agents that work together like a society. Each agent handles simple tasks, and their interactions, organized hierarchically, create complex behaviors, intelligence, and consciousness. Well, to achieve real workflow automation, such as the workflow needed to reliably set up a computational fluid dynamics simulation, it's not enough to rely on one large language model. If we want to avoid hallucinations and handle new environments, we need a flexible architecture that blends neural and symbolic methods together in a hierarchy. Inspired by Barr's global workspace theory, we design the next generation of Guru as a society of event-driven semi-autonomous agents. This is different from the orchestration pattern where a central module decides everything. Here, agents wake up, act, and cooperate based on events, whether those events come from the user, the environment, or other agents. At the highest level, the system is built on 7 core components: data, a growing collection of workflow-specific real-world and synthetic data sets; learning engine, machine learning techniques tuned for scaling, training on supercomputers, like a factory for training a broad range of models and methodologies, producing ultimately decision-making agents. Agents and the agent society, semi-autonomous agents that achieve sub-goals of a workflow. Our rules engine, a symbolic subsystem inside each agent, checking the correctness of inputs and outputs like sanity checks. The workspace, a message pool where agents exchange information with built-in logging, attention, and explainability. A progressive web app, the interface, our universal interface for hybrid user interaction across multiple channels. We built the Guru interface to run in a browser so you could use it from your desktop, laptop, tablet, phone, spatial computing headset. And finally, execution environments, external programs, or even real-world systems that can be controlled by agents and generate new observations. Next slide, please. In this and it's a video, so it should start up hopefully. Yes. In this example of a CFD simulation setup process, once the user provides the geometry and flow conditions, the initial request, Guru takes care of setting up the rest. It begins with performing surface grid generation, then moves on to the volume grid, making sure that the mesh is high quality and proper and achieves adequate boundary layer resolution. Simulation is set up, choosing solver parameters to procure convergence. Then solution adaptive grid refinement is set up to, for example, capture shockwave boundary layer interaction. And if we go to the next slide, we're just showing a few different views of the outcome of that particular simulation that we very quickly showed as one example. Showing how, in this case, NASA's refined code is used on top of the baseline mesh to concentrate grid points in order to capture high gradient physics. The next slide, please. And in this, this is another video. In this video, we're showing what we've been working on adding in Guru Generation 2 in terms of interface options. As much as possible, we want to give a minimalistic view that's neat and clean to the user, like the one that we just saw previously, but also provide the user to access whatever level of detail that they want for their particular work. You're looking, for example, at a series of process and workflow status messages. You're looking at the top left of an actual graph structure that is formed as a consequence of the series of inputs from the user, the series of events invoked by the system, and the status of processing those. Well, agents communicate here in the via global workspace, implemented with MQTT topics. They can live on different compute resources, but still share the same workspace. Even the progressive web app is just another agent. It listens, publishes, and participates. Right now, in the example that you saw here, active agents in the workflow, including the PWA VNC visualization agent for, in the first case, FreeCAD, and then ParaView in the later case. Large language model for structured output and smoothing, a CFD agent that enforces rules and prepares data and launches agents to perform the end-to-end workflow. One running on a separate server to manage containerized tasks, and another on the high-performance compute system to actually submit the jobs. The progressive web app keeps everything alive by sending heartbeat pings across the agent society, discovering which agents are present and building a live topology of the workflow. And we want to visualize numerical simulation results directly from the front end, provide initial views based on the initial request with just halftone dot kinds of images, and then adding more sophisticated images as the user request is fleshed out more. We have integrated a full symbolic rules-based system and are incrementally training more and more agents to achieve vastly more comprehensive workflows. If we go to the next slide, please. In computational physics, geometry is always a problem. And just like it's often more economical to rerun a simulation rather than storing raw simulation data for months or years, it's most common to these days retain the metadata and reduced results and then rerun it later rather than paying to store it on a storage server. Well, likewise, it's sometimes more economical to generate a new geometry rather than fixing the current one. In this particular example, we have been training agents to perform new geometry generation in the parametric geometry creation and aerodynamic modeling tool called OpenVSP. It's it enables us to generate 3D models that are high quality and ready for a CFD model of this type. And for example, we can sample a random text goal describing a type of aircraft, some traits of it, and the OpenVSP agents will actually reverse engineer that request into instructions into OpenVSP to actually generate a new geometry. The similarity is measured in embedding space using the cosine distance. It gives us a way to achieve real parametric geometries that match the target geometry that the user has requested by voice, by typed text, also by target image, or by target geometry that they supply as an initial seed geometry. Let's go to the next slide, please. In tackling sparse data problems, we train predictor agents using multiple containerized automated machine learning frameworks like H2O, CatBoost, AutoKeras, Teapot, AutoGluon, and AutoSKLearn. These frameworks run in parallel, searching for the best performing models in a hierarchical fashion, scoring them against each other, and ultimately training the top ones and competing them against each other in ensemble runs. Once the strongest model is selected, it is wrapped into a predictor agent and integrated into the broader agent society, ready to deliver reliable parameter predictions for whatever use case, such as choosing solver settings for a given flow solver. Next slide, please. And again, at the beginning, I mentioned the executive order calling for truth-seeking AI. Large language models based on transformers in the manner that they exist right now might not get there. Transformer networks process sequential data like text using self-attention mechanisms to weigh token relationships, capturing context globally. A transformer network operates auto-regressively, predicting the next token based on prior ones, trained on large data sets to optimize likelihood. Well, in addition to transformer networks, we use baseline transformers and also patch time series transformers. We also, for a few years now, have been using and training our own joint embedding predictive architectures, or JEPA. The strength of these is that they focus on learning representations by predicting latent embeddings of data. For example, images or video in a shared space. It uses contrastive or predictive objectives to align embeddings, emphasizing invariant features across modalities, not auto-regressive token prediction. Tends to overcome some of the hallucination problems, for example, of conventional large language models. So joint embedding predictive architecture learns representations by predicting latent embeddings of data in a shared space using contrastive or predictive objectives to align features across modalities, focusing on semantic invariance. And we also use graph joint embedding predictive architectures, which is an extension of JEPA to graph structured data, predicting hyperbolic coordinate embeddings for subgraphs. It leverages graph topology to capture hierarchical and relational semantics, optimizing for graph-specific tasks like node classification or link prediction. So if you ask the question, is a large language model going to navigate my file system and then dive into a database and find something for me? And then is it going to perform a series of best practices to massage or remake my geometry and then make some choices to correctly generate the grid and make some iterative comparisons to improve the quality? And then is it going to select the right solver settings to procure convergence for this specific use case? And then is it going to perform a series of tasks to set up a batch job of 100 or 1,000 of those simulations? And then is it going to correctly drive workflows to post-process and reduce that data? Maybe not. This kind of approach gets you closer there and is an essential part of our hierarchical system. So JEPA helps our models learn meaningful embeddings, for example, from CAD data. For CFD simulations, accuracy depends on capturing enough detail, especially potential defects. With graph JEPA, for example, we convert CAD models into graphs, then sample subgraphs for context and target. Encoders transform these into embeddings, and the predictor is trained to minimize the gap between the predicted and target embeddings. During inference, the distance between distance gives us an anomaly score, highlighting defective regions. These embeddings and defect scores then feed downstream agents in order to achieve something optimal. Let's go to the next slide, please. And another essential part of the hierarchical system is how we achieve planning with reinforcement learning. We're showing some scalable examples of training, in this case, across one reinforcement learning driven task scaled across, I think, 1,000 GPUs in that case. We use reinforcement learning to train planning agents that, for example, configure CFD simulations step by step. The agent starts with CAD geometry, simulation goals, constraints identified by the user, for example, or by the nature of the problem, and defect embeddings taken from graph joint embedding predictive architecture. It then selects a variety of parameters like surface grid parameters, volume grid parameters, solver setting options. And each choice improves grid quality and procures higher quality convergence. Observations combine geometrical properties, anomaly scores, past actions, etc., while rewards are given for stable, high quality outcomes. Training is done by distributed or DD, proximal policy optimization, distributed proximal policy optimization, a scalable extension of PPO. We're using PyTorch distributed data parallelism, enabling us to train reliably across hundreds or thousands of GPUs with linear scalability. Next slide, please. Our optimizer agent supports a variety of methodologies for computational fluid dynamics parameter tuning. The one example is sub-goal optimization. We optimize, for example, surface grid parameters for mesh quality, and then those results to optimize the volume grid, and finally adjust solver settings to procure convergence. The next is a high-level goal optimizer, where all of the parameter sets are optimized jointly in a single process against a convergence objective. Together, these approaches give us flexibility, staged optimization for step-by-step control, or joint optimization for efficiency, end-to-end performance, etc. Next slide, please. We use data analysis tools such as explainable boosting machines, feature importance, self-organizing maps to understand what are the important features, what are the biggest drivers in these high dimension parameter spaces, which input plays a more significant role than others in determining the outcomes that we have set as the actual objectives. And we use the self-organizing maps to actually understand the high dimension space by mapping in just a series of 2D squares the behavior, the relevant associated behavior of each individual variable. Gives us a clearer picture of how different parameters influence the outcome. The explainability aspect is especially important because it helps us guide refinements and ensure that we're not doing this as some kind of black box process. These are some of the tools that enable us to gain insights into how to make the model more transparent and drive maximum reliability. Because ultimately this is made for decision making in the autonomous system. Next slide, please. And we are using so-called behavior cloning to train predictor corrector agents. Just like in CFD, there's the classical concept from decades ago of a predictor corrector method. Likewise, a first prediction from some machine learning model or some strategy is not always going to get you there, and so we have built our system to be able to make a first try, evaluate it, learn from what it's done so far, adapt, and achieve something better. This is just one of the examples that we're showing. We compile data sets of state action pairs from expert workflows or simulations. Each state represents what the agent observes, and each action is the expert's chosen response. A supervised learning model then maps states to actions, essentially teaching the agent to imitate expert behavior. In practice, these agents correct parameter settings for surface and volume grid and CFD solver settings, for example, ensuring simulations set up, stay on track, and converge reliably, no matter how diverse the set of simulations that you're setting up. And when we talk about expert behaviors, for example, we're not only talking about monitoring an individual human user, but also learning from video tutorials, for example, also learning from tutorials in other kinds of documented procedures of different forms. Next slide, please. And this is a schematic view of this behavior cloning process that I've just described, actually. Next slide, please. And we use predictive models to estimate the best fit parameters for setting up an execution with the goal of producing the highest quality outputs. However, in some cases, the predicted parameters may fail. This usually happens because of undetectable issues, subtle geometry features or errors in a CAD model, for example. To address this, we introduce a corrector step. The corrector agent adjusts the parameters when a predicted setup fails or or just is not maximally successful, allowing the process to still produce high quality outputs ultimately. In this example, the correction is applied during surface grid generation where CAD models might contain small, undetectable features that affect the outcome. While the corrector agent doesn't directly know what those are, it can recognize the resulting issues in the output and then take actions on the parameters or settings to iterate and avoid them. This way, even in the presence of hidden problems, unexpected issues, the system is still able to iterate, correct course, and maintain robustness and ensure reliable results. Next slide, please. A really common problem is if we were all in a room together, someone would laugh. If I was not the one speaking, I would be the one laughing about how unfortunately common it can be to accidentally set up your simulations so your airplane is flying sideways. So geometry pre-processing is a general, really advantageous thing to be doing, and just pointing the flow in the desired direction is one of them. So we have trained agents to predict orientation. We created a data set of, in this case, vehicles with labeled directions, but we didn't, hand label these. We processed video, sequential video frames of a broad range of flight vehicles, segment the vehicle from the background, and compute optical flow. A model is then trained on this data and then can automatically infer the most probable direction of flight of a geometry. It's, I think, the most flexible manner to achieve this kind of training for the most flexible range of outcomes without having to manually label anything. Next slide, please. So one powerful application of synthetic geometry data sets is training a model to predict parameters directly from a goal. Whether that is expressed by text or an image, it might be a sketch that you sketch, or it might be hand motions that are picked up on the camera. It might be you speaking and describing what you're looking for, or some combination of those. This pipeline works in two stages. First, we use a diffusion model to generate a visual candidate from the description. Then the user's description of any type. Then we embed that image and feed it into our deep VSP model, which then predicts the open VSP parameters, and then we finally generate that geometry from scratch, and then set up any kind of simulations on top of that geometry. And because we're working with parametric models, iteration is simple, and it is, by the way, a beautiful example of large-scale, highly scalable ensemble jobs that you can run on HPC. It enables you to then not just describe what baseline, for example, flight vehicle that you'd like, but how you then would like to modify it. Make the fuselage longer, twist the wings 5 degrees, give me some negative dihedral, sweep the wings back 5 degrees, etc. Next slide, please.
Allan, you actually are just about out of time.
I'm almost. That's good because I'm almost out of slides.
Okay, you have about 1 minute.
Fantastic. And so on the next slide, I'm talking about some essential elements of the architecture. Long story short, we've built a hybrid architecture that enables us to both use symbolic rules. Again, we don't hand label them, but we ingest them from authoritative sources with machine learning to give us flexibility to treat a number of problems. And the last slide, please. Second last slide, but anyway, the next two slides are talking about the agent society. And long story short, these are this is not a central control system. Agents wake up based on a specific request and requirement, and then interact together. At the platform level, we have the interface and the back-end orchestration. Then we have the modular agents that we are able to train and add more and more that then enable us to do vastly increasing levels of sophistication of workflows. And these are some elements of how we accomplish that. Thank you so much. Thank you.
Were there any questions?
One question came in about your web interface interacting with the container on the login node. How do you handle the Kerberos authentication when it comes to accessing the login node?
We with Guru Generation 1, we've already actually deployed that at particularly at AFRL DSRC and ERDIC DSRC in the portal. And so you access Guru once you've already authenticated into the system.
And then one other question came in. Will we be able to download the slide? Oh, I'm sorry, that's probably not for you, but will we be able to download the slide somewhere, and whether we have a demo of the system?
Yes, would be thrilled to. Please reach out to me, Allan at msb.ai. You can spell Allan anyway, but ALLAN at msb.ai. Be thrilled to set something up.
I don't see any other questions in chat, and as we said, we're out of time. Let's see, one more just came in. We'll call this the last question of the day. For simulation-based optimization, is there any evidence that the agentic approach is more efficient than available black box solvers?
So this way gives you way more options to achieve a couple different things. Number one, score the reliability of each individual agent for each individual type of task, and also you can add more and more collaboration on top of these agents. So at first you might just say, oh, well, I would really like to save a lot of time and not have to hunt and peck through the interface to find the thing I want to do. And so I would just like to automate the setup of a configuration file. But once you have that, then you start getting greedy and you start saying, well, actually I would like to do that 100 or 1,000 times because I want to run an entire aerodynamic database, or I want to run a series of design modifications. And then when you have that, then you start getting greedy again and you say, well, I would like to add more agents to understand on a top level, on top of all those results, to tell me how to optimize the design across the entire flight envelope. And also I would like to then train the system to learn how to fly that vehicle autonomously. Well, if you have this kind of agent-based approach, you just keep on adding more and more agents in a hierarchy and achieve vastly, increasingly more sophisticated workflows, and you have a measure of the reliability independently of each one before you're registering in the system. If you don't do that, then you very quickly can have errors pile up and not even know where they are and not know how meaningful or not the result that you're getting out of what you're trying to accomplish. So I think there is that sort of advantage.